in your class? Good. Okay. You must practice the problem on it. Today I shall start the compensation. You do not, if you do not understand, you must ask me because this is the backbone of our system operation. So, reactive, the topic is the reactive power compensation. Compensation means to fill up something, you know. So, what to compensate? Actually, in power transmission system or in any system, if we talk about the power, we can only compensate the reactive power. A capacitive current can be nullified by an inductive current, or an inductive current can be nullified using capacitive current. But it is not possible for active power. Active power cannot be nullified by anything. Okay, we cannot reduce load by, we can reduce load like by these passive elements. We need in that case only the generation. So compensation means always the is means actually the reactive power compensation. So why compensation is required? Actually, the concern of power transmission line operation is its voltage drop. If the power load at receiving end increases, then the voltage drop across the transmission line increases because the V equal to I into Z. Now, if we could keep the voltage drop constant or as low as possible, then we could be able to maintain higher voltage at the receiving end. And if we think about the constant power devices or constant power loads at receiving end, in that case, it would draw the less current through the transmission line. So it will be profitable for the power transmission system because less current flowing through a transmission line, even at high power condition, will produce less transmission line loss. So efficiency will be more and the profit will be more. So that's why the voltage drop in a power transmission line is concerned. But we cannot make it zero because the current will flow through a resistance. So obviously there should be some voltage drop. We only can minimize it. For any transmission line, generally we represent the transmission line by its reactance only. I hope you can remember that representation of long transmission line. If we assume that R is very very less than L, in that case, even if in long transmission line representation, we can represent the transmission line only by a series reactance. Then if we think in that way that transmission line resistance is very low as compared to the reactance and transmission line is represented by only its reactance, then the expression the figure then a two bus transmission line, two bus power system will be as shown in figure. So what will be the power at receiving end? At receiving end power. So here you see at receiving end I have shown two types of power, PD, QD, PD plus JQD and PR and JQR. There is a reason for it anyway. So PD plus JQD is the power which is demand from the consumer end. And PR plus JQR is the power that is supplied by the transmission system. So if it is ideal case, then PD plus JQD obviously will be PR plus JQR. I have differentiate here. At this moment, we can assume both of these are same. Now, what is the power transferred by the transmission line? That is PR plus JQR, right? Do not get late. So, PR plus JQR is the power transmitted by the transmission line. Have I shared the screen? So PR plus JQR is the power transferred by the transmission line. This demand may be more than that, but transmission line is able to transfer only this much of power. That's why I have written this two in different notation. So what is the power at receiving end? Obviously VR plus IR conjugate equal to PR plus JQR. So from there we can find out the expression of current. Now what is the voltage drop? Voltage drop will be line impedance into the current through the line. Since here we are considering only the series admittance, series reactance, so IR will be equal to IS. So whatever the voltage drop will be JXIR. So if we put the value of IR, then we shall get this expression. You see here there are two terms. One is real part, another is imaginary part. Real part is dependent on Q, whereas imaginary part is dependent on PR. Real part I have termed as delta V dash and imaginary part as delta V double dash. I shall not allow anybody else. I would. So if we draw the phasor diagram, so this is the voltage drop. So the receiving end voltage plus this voltage drop will be the sending end voltage. So del VR plus del V, VR plus del V will be equal to Vs. Now this del V has two components, V dash and del V double dash. Now for power transmission line, generally this delta is very low. If delta is very low, then Vs is much near to the VR, near to the phase of VR, but it is higher than VR. Then which component will be higher, more among this del V and del V dash, double dash and del V dash? If delta is very, hmm?
Del V dash.
Del V dash. That means now why delta is small? Actually, we keep delta small so that actually this is related to the generator load angle. So if we keep it small for the normal operating condition, then we can tackle the faulty condition. Otherwise, not. So generally for interconnected power system, large interconnected power system, delta is generally kept within 30 degree. For normal load, it is 15 to 20 degree. So del V actually more than del V dash. So in the among these two components, this is more dominating for power system. So del V dash is due to this QR. So obviously on the actually the voltage drop is controlled by reactive power more as compared to the active power, because imaginary part is controlled by P and real part is controlled by Q. So voltage drop approximately we can write approximately equal to del V dash, so X QR by VR. Now obviously if QR is increasing, then the voltage drop will increase. Why QR will increase? To increase in due to increase in load. If we want to send more power, then QR will be increased. Then how we can make this controlled? Now QR will be increased even there be high increment in PD, that means real power of load, because in that case also current to the transmission line will increase, so it will increase the reactive power, right? So change in voltage magnitude at any bus is strongly coupled with Q. That means when there is a change in Q, then the change will be more. Say for 20 megawatt change in P, if the voltage change is 1 volt, it may happen for 20 MVA change in Q, the voltage change may be 5 volt in that way. Now, how we can make the compensation? So QR actually is controlling the voltage in the transmission line, right? Now at receiving end, if the load is increasing, reactive power by any means is increasing, then we may add one compensating device at receiving end. Now net load at net power at any node will be constant. So if we consider for reactive power at receiving end, then QR should be equal to QD plus QComp. QD and QComps are connected from the load side, and QR is received from the sending end as the power transmitted, right? Now you see here there is a del V for a del QR. Now del QR, what is QR? Say normally there at ordinary condition there is some QR. Now load has increased. Now that's why the QR has increased to QR dash. So QR dash is more than QR, right? So for that reason, this del QR will increase and this del V will also increase. For a particular value of QR, there was a voltage drop. But due to enhancement in QR, this del V dash or del V will be increased. Now, if we want to maintain this del V constant for any value of QR, in that case, we have to make this delta QR constant. So, load has changed from QR to del QR. Now, it's actually, if we want to maintain same voltage drop, so the deviation in voltage drop will be zero if the del QR is zero. Then whatever be the change in reactive power has happened, that should be compensated locally. Then we can make this one as constant. That's why a reactive power compensating device is connected at the receiving end in parallel. That's why shunt compensation. So QR equal to QD plus QComp or QComp equal to QR minus QD, right? So if there is no change in demand, then QR will be as same as the actual load was. So say initially the load is say 10 plus J5. So if there be no change in demand, they say that for that reason there is a voltage drop of 10 volt. Now if there is no change in load, then there the voltage drop will remain as 10 volt. Now if we assume that voltage has changed to 20 plus J15, right? If we go for approximation, we have seen that the effect of change in real power is less as compared to the reactive power. So this additional 10 MVAR Q will try to increase this 10 volt, obviously will increase. Now if we want to maintain 10 volt as it is, then virtually we have to maintain this 5 MVAR at receiving end as it is. How we can make it? We just said minus J10. How? By inserting a capacitor. So this is the concept of compensation. If you do not understand, you must ask me. Then Q compensation is QR minus QD. So QD, if the QD is same, that means for a particular value, then there will be no need of Q comp. Now say whatever QR required here, the QD is more than that. That means demand is very high as compared to the QR. That means reactive power supplied. Then what will happen? It will create the under voltage problem, because in that case actually from the receiving end side delta QR is high from the load side. So it will create under voltage problem. So to maintain voltage to the actual value or to the rated value, we have to add some capacitive compensation, because in that case we have to reduce this Q comp is coming QR plus QR minus QD. QD is negative, so it will come negative. So capacitive compensation in that way, mathematically. Physically, if the heavy loading condition means inductive load. So if the inductive load is there, it will create an under voltage problem, huge inductive load. Then in that case we need capacitive compensation to compensate that one to maintain voltage to a certain value. So the compensation does not makes the voltage drop in a transmission line equal to zero. Rather, compensation helps the power transmission operator to maintain a steady voltage drop, steady voltage drop in the power transmission line, even at over voltage overloaded condition, that means under voltage condition. Similarly, when there is a low load condition, say there is very low load as compared to the rated load, or there is a no load, that is like Faraday effect. So in that case QD is much less than Q comp, so it will come negative, so there will be a voltage rise in the system. So in that case, obviously there will be over voltage problem. So with that problem, we should tackle with the inductive compensation. Like so this thing you have already learned that in case of Ferranti effect, we use shunt reactor to control the Ferranti effect to maintain the voltage level within a certain range. The VR should not be much higher than Vs. So this is the concept of shunt compensation. So this is very simple way that using capacitor in parallel or inductor in parallel, we can we can maintain the desired voltage drop in a power transmission system. But there are some other compensating devices which may give some other advantages. But the main purpose is same, that it will only compensate the reactive power at the receiving end, either in the capacitive way or in the inductive way, so that the voltage drop can be maintained. Now, when we are connecting a compensation at the shunt as shunt at the load end, so it is and just for that particular load or just for that bus. So it is called local var generators or local compensators. There are three types of that. One is shunt capacitor or inductors, that is conventional one. Second is synchronous condenser, and another is the SBC, the static Var Compensator. SBC is a power electronics control device where we can change the capacitor controlling the thyristor gate switching. So in this case, if we use a conventional capacitor, then for every load change, we have to manually adjust the capacitor so that compensation may be perfect. But it is not possible actually in power transmission system. Then it will be in steps. A capacitor change will be in steps. So nowadays, to make it smooth, so it will automatically sense if there be voltage rise or drop, and it will automatically switch on the capacitor or inductor in that way. So that advanced device is the static var compensator. This is a primitive fax devices also. Fax device is called flexible AC transmission system. Why flexible AC transmission system? Whatever we are learning now from the third year first sem, all are AC system. Now in AC system, main issue is this the reactive power capacitor and inductor. Active power is required, the consumer will pay for that. But reactive power, we have to tackle that so that we can transmit as much as possible max active power to the consumer end. So that's why flexible AC transmission system is a the ideal power transmission system where we can tackle the reactive power by different way. So that one primitive fax device is the static var compensator. Now, what may be the problem with shunt compensation? Shunt compensation, if we can connect a inductive compensation, then transmission line has a shunt capacitor. So in that way, it may create the parallel resonance. Similarly, a load is a inductive device. We are connecting capacitor, so it may also create parallel resonance. So that is the problem. And if we connect the shunt compensation just uh, arbitrarily, then during under voltage problem, if we connect a inductor, then it will create further under voltage problem. Or if we keep a capacitor connected under during under voltage condition, now suddenly load has thrown off, then that capacitor will create the over voltage problem. So that problems are there. Now capacitors and conductors, inductors, I am not discussing. Let us discuss synchronous condenser. Condenser, the name is condenser because here it is acting as a capacitor. Actually not capacitor, it may act as a inductor also. Since it is called, anyway, it is called synchronous condenser. But actually it is not a capacitor, it is a machine. It is a synchronous machine, synchronous motor at no load. So it is a rotating machine, a simple induction synchronous machine. So how it can be used as a compensator? It is a synchronous mode, special in the synchronous motor where its excitation can be adjusted. Now, if we write the current equation, then current through the synchronous motor, SCA synchronous condenser, then VR minus E by JXS. VR is the terminal voltage and E is the excitation voltage. So from there we can find out what is the expression of reactive power produced by the synchronous condenser. One thing I must mention in the compensation, that capacitive compensation does not mean capacitor is supplying any current. Any capacitor never supply any current to the system. Actually, it is supplying, it is taking some capacitive current and it is taking some inductive current, which are 90-degree out of, which are 90-degree out of phase. That's why they are compensating. So compensator does not means it is supplying something. It is actually drawing, but it is drawing in a in such a way that it is compensating the load. So, for synchronous condenser, this will be the expression of the expression I am not reading. You can understand it. So, from the you just read go through it later. So, compensation, the reactive power of the synchronous condenser, the expression is this one: VR into E minus VR into X by XS. So, this QSC will be greater than 0 if E greater than VR. We have taken voltage conjugate. You see, we have taken voltage conjugate into current. Why voltage conjugate? Because current has a negative in a algebraic form. That's why voltage conjugate. For algebraic form, we generally do not take the conjugate. So that's why the positive imaginary part will give you the capacitive var, and negative imaginary part will give you the inductive var. So when E is greater than VR, then this QSC will be positive. So if we want to configure the synchronous condenser as a capacitor, then adjustable excitation should be made in such a way that E is more than VR. Okay, so that is actually over-excited condition of synchronous motor. Similarly, if we want to make it as a inductor, then E should be less than VR. So under-excited condition. So these are, in this way a synchronous motor can act as a synchronous compensating device. It is name is industrial name is synchronous condenser. Now how we can differentiate one synchronous motor from a synchronous condenser? This question generally asked in grand viva or interview. Say synchronous, the condition of synchronous operation of synchronous motor as a synchronous condenser is that it should be at no load. So there will be no mechanical loading on the motor. So if we want to omit the provision of mechanical loading to a motor, then there will be no projected shaft. That's why for synchronous condenser, there will be no projected shaft. But for ordinary synchronous motor, there should be projected shaft because that will be mechanically loaded, right? So in this way, you can visually say which synchronous motor can be is in synchronous condenser and which one is not. Okay. Now, what is the advantage? So here, by only by excitation control, we can get both inductive and capacitive type of compensation. But the disadvantage is it is costly. Installation is tedious. At the same time, it requires a regular maintenance because it has rotating parts. So bearing, all these things are there. So lubrication and all other maintenance will be required more for the synchronous condenser. Otherwise, it is a very good compensator because we can get wide range of compensation from inductance to capacitance very easily. Next is static Var compensator. It is a power electronics based device. Just see, this is a transmission line, right? So there will be actually a set of capacitor, set of inductor connected in parallel within the SVC. So obviously, by combination of these C's and L's, obviously we can get either inductive current or capacitive current, and that is also controlled by thyristor valves. So it is possible to get smooth controls. So this is the static var compensator. Then why this coupling capacitors, PTs, all those things are there? These complicated things, because this power electronics part or this SBC part are low power device as compared to transmission line. So it may be in transmission line may be in 132 kV, it may be 10 kV or 230 volt. So in that way, we need a transformer. And how this capacitor or inductive current will be controlled, so that's why some reference and some control will be there. So this is the control. So there must be some V reference at which voltage we want to set the bus voltage. It will be compared with the available bus voltage, and accordingly the capacitor and inductor will be switched on. Here it is written static bar compensator employing thyristor switched capacitor, thyristor control reactor. That means here in the capacitor side, thyristors are only used as switch purpose, and inductor it is used for the current control purpose. Static bar compensators directly not in your syllabus, but it should be known in the undergraduate class. So I have discussing this one. So this is the static bar compensator. So in short, actually, what is static bar compensator? There is one adjustable capacitor and parallel with adjustable inductor. Why it is not shown the other side? Because this is for per phase representation. This SBC will actually have the three phases. So actually, what happened? It is the if this is the inductive current, this is the capacitive current. So either controlling these two, we can get zero compensation or capacitive compensation or inductive compensation. So this is the concept of SVC. Next, compensation is also required to control the power flow through a transmission line. So whatever shunt compensation I have discussed till now, say static bar compensator, the synchronous condenser, or just ordinary inductor or capacitor in parallel, in all cases the purpose was to control the voltage, to maintain the transmission line voltage drop to a specified value. Now you see, if we want to find out the expression of power flow through a transmission line, then if similarly, if we can find out the expression of current, Vs minus Vr by Jx, so we are assuming that Vr is the reference phasor, so Vs at an angle delta minus Vr by Jx. So we can separate it in real and imaginary part in this way. So what will be the total power? VRIR conjugate. From there, we shall get two parts. Then you see the real part only. So real part actually depend on x and depend on delta. So if delta is more, then we can get more power transfer. So for a particular value of transmission line reactance, when delta equal to 90 degree, then we can get the maximum power. So it is Vs Vr by x sine delta, right? So what is the maximum power? So maximum power is this much. So this much will be maximum value of power. So now this maximum power we can get when delta equal to 90 degree. Otherwise we shall get something less. But if we want to maximize this, what is the option? Then we have to reduce this x, right? That is only option. How we can reduce this x? If we connect a capacitor here, that is only one option, right? So, if we want to increase the power flow through a transmission line, then we have to connect a capacitor in series. 1 minute. So, actually PR is VR Vs by X sine delta and QR is VR Vs by X cos delta V square by R. Then if we want to maximize it, then we have to connect a capacitor that I have explained. That I am not writing XC, but I have written XCOM. That because we are compensating it. So what will be the effective reactance? X minus XCOM, obviously. Now, if we assume that XCOM, that compensation given, is a certain percentage of the line reactance, then it is called K. So K is called degree of compensation. So K may be 0.2, zero point 0.3, ideally it may be 1 also. Then effective will be 0. So in that case, if we consider this one, then the infinite power will flow through the transmission line. So this K is called degree of compensation, but we never make K beyond 30%. Because if we make K equal to 1, ideally X effective will be 0. So the infinite power will flow through the transmission line, but at the same time that will be the resonating condition. So at the resonating condition, all the power will be absorbed by the transmission line. No power will be sent to the load. So receiving end will not get any power. PR plus JQR will obviously be maximum, but that will totally lost as a I square R loss in the transmission line because it will create a resonating circuit. So the load circuit will not come then. So we never make series compensation 100%, and we never make series compensation inductive. Because if we make series compensation inductive, that means it is plus, then it will make the x more. So V1, V2, VRVS by x and VRVS by x, that value will be further lower. So that is of no use. So there is no concept of series inductive compensation uh, for power transmission system. So what are the problem associated with this series compensation? One is series resonance may occur if we make the over compensation, and at the same time there may be mal-operation of distance relay. What is distance relay? Actually, relay is a device which can sense the fault of it in a transmission line, and distance relay measure impedance from a point. So if you connect a shunt capacitor, then series capacitor, then the impedance of the line will change. So say a distance relay is set that if the line impedance is less than 20 ohm, it will operate. Now using the compensation, it has made less than 20 ohm, but it will sense it as a fault. Then it will operate because fault means low impedance path. So it will sense as a fault and it will trip the circuit. So that's why there may be mal operation of distance relay. The special care should be taken for that. But this is so power for the purpose of series compensation is mainly to improve the power transfer capability of a line, because it is increasing that VR Vs by X effective part. That means Pmax is increased. But since we are compensating reactive power, we are compensating reactance, then obviously the voltage will also improve. But there will be no such relationship like the shunt compensation will be available. But series reactive compensation will also improve the voltage profile, because actually it is improving the reactive power status of the line. At the same way, when we are using the shunt compensation, that means we are actually improving the receiving end voltage even at loaded condition, because we are controlling the voltage drop in a power transmission line. So actually shunt compensation will also improve this power transfer level of the transmission line, but not in directly in this way. So actually series compensation is directly coupled with the power transfer of the transmission line, and shunt compensation is directly coupled with the voltage regulation of a transmission line. But it does not, they also perform vice versa. The series compensation also control voltage drop, shunt compensation also control power flow. Now, the voltage control may also be made using the on-load tap changing transformer. What is that? On-load tap changing transformer is a special transformer where the load tap can be changed during on load condition, right? So when we are changing the tap, actually we are opening a series circuit and connecting. So there is a methodology for that through which we can do it. So actually, say for 100 volt on the primary side, 110 volt is available at the receiving end. but due to change in due to load in receiving end, say voltage requirement is high. So for 100 volt at the primary side of sending end, we can make the receiving end voltage 120 by only changing this tap. That is the concept of on-load tap changing transformer. And taps are always provided on the high voltage side of the transformer. For the sending end side, the line side is the high voltage. So secondary is the high voltage, so tap is the secondary side. For the receiving end side, the primary side is the line side, so high voltage side. So primary side is with the tap. So what is the purpose of the OLTC transformer? Obviously, to maintain same voltage at the even at the overloading condition, or don't want to change the sending end voltage setting, but same voltage drop will be maintained using the OLTC. Now, if we go for derivations, what derivation? Say here we assume that normal tap is NS. Now there is a taps are like 5%, 10%, 20% in that way, 10%, 15% in that way. So so actually what is happening? If the primary voltage is 1, if you are setting the tap in the secondary at 5%, that means you are getting 1.05 um, voltage. Similarly, for 10%, 1.1 voltage. So whatever the actual trans ratio of the transformer, that will be multiplied by the tap ratio, tap setting. So this is the for the sending end, the tap ratio will be 1 is to NSTS, and for the receiving end, it is NRTR is to 1. TR will be multiplied with the actual offload of nominal tap ratio. NR is the tap ratio when the trans ratio when the tap is at the lowermost condition. There are two terms, tap ratio and the trans ratio, or the tap condition and the trans ratio, tap position and the trans ratio. Now you see, when there is no load, so that line can some current may flow through the transmission line only due to its capacitance and inductances. So at no load condition, there will be no requirement of taps. So TS is at the 1 condition, so it is 1. So Vs by 1 equal to V1 by Ns. What is V1? V1 is the secondary side voltage at the sending end. So we are assuming that V1 equal to NSVS. Now NSVS is assumed as a parameter of E. Similarly, at the receiving end, V2 by NR will be equal to VR by 1. So from there, V2 will have equal to NR VR, that is equal to E. Why E? We are assuming at this condition voltage drop is 0. So there is both side, it is E, right? So this will be the voltage at the uh, no load condition. Now say at a loaded condition, when there is a load at the receiving end, so in that case V1 will not be equal to V2, some current will flow through the transmission line, so del V equal to V1 minus V2. Now taps are always chosen as a reciprocal ways. Then in the power transmission system, this is required. Otherwise, we cannot maintain the voltage. So now what will be the voltage drop? If you forget about transformers, then this part only a short transmission line. This part, then what will be the voltage drop through it? IRR cos phi r plus IRX sin phi r. So in that way, the voltage drop is IRR cos phi r plus IRX sin phi r. So phi r, right? Now phi r is the power factor of load. Now you see in between the receiving end load side and the line side, there is a transformer. So if we assume there is no such phase change from transformer primary to secondary at receiving end, then we may assume that the phase of this current is same as the phase of receiving end current. So this is IR at an angle phi r, and this is I at an angle phi. Here phi equal to phi r, that we are assuming. Then due to MMF balance at receiving end, if receiving end there be an MMF balance, current is in the primary side I into NRTR, in the secondary side I. So I into NRTR equal to I. So from there we are getting an expression of I. Why it is required? Because voltage drop is in terms of I, because IR is not directly related to voltage drop of the line, but I is related. But we need the expression of voltage drop in terms of IR, then we can relate it with the taps, right? For that reason. So I can be converted to IR in terms of IR and NRTR. So just put it there, right? Now you see active power is VI cos phi, reactive power is VI sin phi. So from there, in the expression of 6, this was the expression of 6. You see, this is IR cos phi r or IR sin phi r we can replace. Why replace? Generally, P and Q are directly known instead of current. So that we can directly relate the voltage drop with the receiving end demand. So P delta VR is simply PR QR plus this expression QRX by VR NRTR. Now we have already seen at sending end, this was the relation, and at receiving end, this is the relation during loaded condition. So what is the voltage drop at loaded condition? That V1 minus V2. So in terms of that NSTS and VS. Now if we compare these two equations 7 and 8, these two should be equal. So from there we can get one expression of T, right? Putting the condition that Ts equal to 1 by Tr and NSVS and NRTR equal to E. From there we shall get one expression of Ts. That means what will be the sending and tap ratio so that we can maintain the voltage drop in a transmission line, right? And if we get Ts, then we can similarly find out the Tr, because Ts and Tr are reciprocal to each other. Now, if I give an example, it may be more clear to you. We have to find out a transformer tap ratios, obviously for OLTC, if the sending and receiving end voltage is not to change from its no load value. When the line delivers a receiving end a three-phase balance load of this, that means whatever be the no load voltage setting, that will be there. But the load has been changed to 16 plus J12. So actually E is the no load voltage value. So here are all the things are given, R, X, E, P, Q, all are given. Just you put the expression and find out T and then find out Ts. So here it should be noted that phi greater than 0 for lagging power factor. If you can remember the derivation of the um, short transmission line, the derivation of voltage regulation, and phi is less than 0 for the leading power factor, because accordingly you have to put that. And the Ts is greater than 1 and Tr is less than 1 for the voltage drop compensation. So in that way we can find out that what will be the tap setting of a way of the OLTC both at sending end and receiving end side if we don't want to maintain the same voltage what was at the no load condition. So the voltage is 132 kV. Only by changing the voltage, the tap ratios, we are maintaining the same voltage drop, right? Otherwise we have to change the 132 kV to some higher value. Sometimes it may needed that high very large tap ratios for higher voltage drop if the voltage drop is more, but it may not be possible. In that case we may need some other voltage drop the compensation means also. Next is the booster transformer. So regulating transformer may be connected. This regulating transformer may be connected at the end of the transmission line and at the sending end. But this OLTC is the construction is very difficult, and for that reasons its cost is very high. It is not possible that every Every 50 kilometer, you put a OLTC and improve the voltage drop in a line. It is not possible. And for a long line, it is not possible to maintain a voltage drop within a desired value. It may be high voltage drop which is not controllable using OLTC uh, by tap changing only. So in that case, we may take the help of booster transformer. What does booster transformer do? Booster transformer actually insert some series voltage in the line. Say this was a line. There was a voltage drop of 10 volt. Now due to huge current, now voltage drop has been increased to 50 volt. Now just if you add one voltage drop in reverse polarity of 40 volt, then you can maintain the same voltage. This thing has can be done using booster transformer. Now the voltage with negative polarity can only be added using a transformer. If the transformer secondary is there with proper polarity and primary you energize, then only it is possible, otherwise not. So this thing is actually done using this booster transformer. So this is the booster transformer. I go to the first figure later. This is the booster transformer. So it may happen that voltage drop is not required, as I have given the example. So there is a 10 volt voltage drop and that is acceptable. So when the condition of 50 volt voltage drop will come, in that case we need the booster transformer. Then how we can connect? We can connect it through a switch, the compensation, like this way. So when 10 volt is there, then this switch will be closed, this booster transformer will be bypassed. And when there is a 50 volt voltage drop, then this switch will be open. Then this transformer secondary will come into action. So these things are done using relay R and S. This is the current relay. With current transformer, every time current is monitored, right? Now, when current is beyond a desired value, so why voltage drop will be more? When current is more, when current is more than a desired value, then this current relay operate. Okay, current relay actually operate when R is closed and AC is open. Normally, R is normally closed and AC is normally open. Now, when current relay operate, then R gets open and AC gets closed, then booster transformer come into operation, right? Now, from the first picture, I wanted to show that from main transformer through transmission line, power is transferred to a particular load. And from in between that, there may be tapping or there may be substation. Now the tapping is there, so through feeder at the regulating transformer, we can increase the load, increase the voltage level. But at the same time, when the voltage level still are not as per acceptable value, then we can increase the voltage level using booster transformer. And booster transformer can locally increase the voltage level and very easily. So that is the use of booster transformer. Booster transformer is for local use, instantaneous use, not for the regular use. Because using booster transformer or regulating transformer, actually we are using more inductive reactive power. And voltage drop is due to inductive reactive power. So using a device which draws inductive reactive power, we cannot compensate voltage drop in a better way. That's why its application is always limited. So this is the three-phase type concept. Now what is the thing? Say for one booster onload tap changing transformer, the current is 33 ampere, 100 ampere and voltage level is 33 kV. Then what will be the rating? 33 kV into 100 ampere, that MVA. But for booster transformer, say if you want to increase 100 volt voltage and current is still 100 ampere, then your volt ampere rating will be only 100 volt into 100 ampere. So rating will be very low. So the transformer cost will be lower. So that is one advantage of booster transformer. So at every point of the transmission line where the voltage drop is required, We do not go with the booster onload tap changing transformer. Sometimes we go with the booster transformer also. So this is the compensation. What thing we need for the further classes? The concept is that when we want to control the voltage drop in a transmission line, we need a shunt compensation. This is the first concept. Now, shunt compensation will be capacitive when voltage is very low, power is very high. The over heavy loading condition, under voltage problem, in that case, we use the capacitive compensation. In very easy way, that load is very high. Load means inductive load. So, inductive current we have to compensate by capacitance. On the contrary, when the load is low, that means inductive current is low, then in that case, how we can increase that? If we want to make go to the local normal condition, we have to connect some more inductor. So the compensation will be inductive. So this much gist is required for the further classes. And using series compensation also, by inserting a capacitor in a series with the transmission line, we can also compensate both reactive power and the power transmission to the transmission line. Power transmission is better controlled by using series compensation, but series compensation always has a restricted use because it has it can create series resonance, and it has one operational issues also. A transmission line through which 1000 ampere current is flowing, you have to connect a capacitor there. You cannot just open and connect, you have to use a bypass for that, is not it? Then only you can connect. So the connection is also not very easy because we have to insert some device in series. So these are the limitation of series compensation. Series compensation are generally rarely used only for the purpose of the increment in power transfer capability of the transmission line. But shunt compensations are randomly used every time as per requirement of power system because it is very easily, it is locally connected and locally disconnected. So this is the compensation. That's all for today. Next class I shall start the uh, the power circle diagram. So for that, it will be better if you sit with a pencil compass and scale. Okay. Then because it is online, so I only shall demonstrate, and through PPT I can show it very fast. But you have to grasp up, you have to do it your own. Okay. So it will be better if you sit with one pencil compass and the one scale. You have to draw some circles using some one set of axes, only that much. The graph paper is not required, pen paper is sufficient. That's all for today. You write your name and roll number in the chat box. All of you have written. I am taking the attendance.